Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is module 13, lecture number 59, designing with Geofoam. I will now focus the recap of the previous lecture, is comparison of conventional and the Geofoam embankment, development of Geofoam in geosynthetics family, EPS Geofoam manufacturing process, and some major application of Geofoam. Now, what are advantages using the Geofoam? Geofoam offer the following benefits. Transport costs are very low because it is a lighter material. Higher and steeper embankment can be constructed. Smaller excavation and reduce structural support. Faster construction and easy of installation. Because it is a super light material, I say that 1 mole is about 2 meter by 1 meter by 0.5 meter, it weighs about the 36 kg. So it is very also easy to handle and install. No mechanical fastening necessary. Help protect against the frost, heat and stress from expensive soil movement. No special equipment for installation. Saving for simplified design, handle and install easily, save time and labor. So you don't need any skilled labor, unskilled labor can also install the Geofoam material. Relief of hydrostatic pressure. It is a lightweight and factory fabricated panel. So as you like it, you can have it, and also you can have it in different density. Low material cost with respect to piling, foundation and insoluble in water. So every material has an advantage as well as disadvantage. This Geofoam material also have certain disadvantages. This exposure to ultraviolet light causes discoloration and protect the Geofoam within the 6 months. And combustible, it should not be exposed to open flame as well as protect the Geofoam from petrol, diesel oil and no resistance to organic solvent. So one has to be taken care for the use of the Geofoam material. Sometimes it is also the use for any construction like that embankment, and if there is any fire, then contractor will be the responsible for this and he has to pay for that. Because one has to be very cautious about the use of the Geofoam from firing. And if there is any petrol is passed through the road, then it is necessary to protect the petrol or the diesel by providing some impermeable material in order that petrol or diesel cannot be passed and should not be destroy this geofoam material. So these are the some of the issue you have to keep it in mind. Sometimes also it has been observed that some ants make a hole and build a room into the geofoam material. And if it happens also, some chemical treatment can be provided to protect the geofoam material. Nowadays also some alternative geofoam material is also coming up. So in terms of the cost, most of the time it has been felt that geofoam material is costly, but I say this concept is totally wrong. I will show you some slide where you can think about that what should be the overall cost of the project, and if you adopt the different kind of the system, and you ultimately prove that which will be the faster and which will be the more economical as well as the stable. So comparison of cost for various ground improvement technique as performed by BASF 2004, the expanded polystyrene geofoam technique offered significant cost saving considering the cost of overall project in terms of future repair and maintenance. So you can see this comparison cost of construction method. So this is the basic on the data of the Korean Highway Corporation, and this reported by Chang 1994. You can see that this is the cost ratio in percentage, and this is the preloading system what we generally adopt for any ground improvement technique. So here is 25% is for maintenance work during the 10 years. This is 38%, and this is 20% for the equipment cost, and then this 7% is the labor cost, 7% is the labor cost, and this is 5% is the alternate cost. So you can see that what are the cost for the preloading, but overall you can have this cost ratio about 95%. But if you adopt the sand-in method, whereas 40% is the maintenance work during the 10 years, and then this is the 20% for the equipment cost, and this is the 43% is the labor cost, and this 7% is the material cost. Whereas if you adopt this is the geofoam system, so here you require only the 40% that labor cost. So you can see that with this three system, whether it is a preloading and then sand-in method and the geofoam method. So geofoam method is cost ratio is 40%. So it is drastically reduce the cost for the ground improvement if you deploy this geofoam material, which is a superlight material. Farnsworth et al. 2008 compare the construction time and performance of three types of the technique. One, MSE or mechanically stabilized earth wall supported by lime cement column. In this system, the time for construction is about 12 months and settlement after 10 years is 137 millimeter. Number 2, mechanically stabilized earth wall with prefabricated vertical drain or PVD or weak drain or band drain installed and surcharging. In this system, time for construction is about 14 months and settlement after 10 years is 112 millimeter. And number 3, expanded polystyrene embankment or the geofoam embankment is made with the geofoam. In this system, time for construction is about 4 months and settlement after 10 years is 76 millimeter. So, you can observe here with these three different systems and you look at the time. So, when you are adopting the mechanically stabilized earth wall, your construction time is the 12 month. When you are using prefabricated vertical drain with the mechanically stabilized earth wall, this time is about 14 months. On the other hand, you can see that when you use only geofoam or the expanded polystyrene material, the time is only 4 months. So, time can be drastically reduced and you know that time is money and also is in terms of the settlement. And in case of the mechanically stabilized earth wall supported by the lime cement column, the settlement after 10 years is 137 millimeter, whereas in case of MSE wall with prefabricated vertical drain, the settlement after 10 years is 112 millimeter. But if you simply use the expanded polystyrene material, the settlement after 10 years is 76 millimeter. You can see that how this dramatically reduce the settlement by the inclusion of the geofoam material. Now, here that it shows that technique what you use 1, 2, 3, time for construction month 12 month, for one technique, 2 techniques is take 14 month and 3 it is 4 month, and in cost for technique 1, $1,60,000 and for technique 2, $1,10,000 and technique 3 is $1,20,000 and settlement after 10 years, technique 1 137 millimeter and technique 2 is 112 millimeter and technique 3 is 76 millimeter. So, look that geofoam embankment had best performance in terms of the settlement and rapid construction time consideration. Even then that it is little bit higher than the technique 2, but in terms of the settlement and the performance, this geofoam material is the best. Now, as you have known that when we use the geosynthesis material, and that material also has a different function like a separation function, reinforcement function, filtration function, drainage function, sealing function, erosion control function, etc. Similarly, the expanded polystyrene or the geofoam have a major 6 function. So, 6 major functions of the geofoam are as follow. This is a lightweight fill is a function. Compressible inclusion, thermal insulation, drainage, structural, and noise and small amplitude vibration damping. I have also showed you earlier that how this material has been used for the different function, where the construction for embankment, where it can use as a lightweight fill material, or at the back of the retaining wall, where the geofoam material act as a compressible inclusion, or where there is a storage or temperature control, how you can use that thermal insulation where geofoam is used. Also, the geofoam material itself can act as a drainage material. Also, that any structural aspect also, and also noise. I say that how you can use that as a noise and small amplitude of the vibration damping at the ground. Now, application of geofoam as a light fill as follow: road and embankment, slope side fill and back fill, vertical face fill and back fill, geofoam wall and railway. Application of geofoam as a compressible inclusion are as follow: you can use behind the retaining wall, beneath the slab or beam at foundation, above the tunnel, pipes and the culvert. Application of geofoam as a thermal insulation are as follow: below ground wall of structure, retaining structure, foundation, that is footing, earth retaining structure, pavement and railways, underfloor area of structure and clay liner. Application of geofoam as drainage are as follows: geofoam can act as drainage to drain the water and the gases in retaining wall and landfill respectively. Application of geofoam as a noise barrier and small amplitude vibration damping are as follows. So, geofoam can control the ground vibration developed by the train, vehicle and aeroplane. Now, application of geofoam as a structural are as follow. So, geofoam can be used as a facing panel for the mechanically stabilized earth wall. That means geofoam can act as a facing panel itself. So, you can construct the geofoam wall, and some also work is going on this related area too. So, this is example 1, characteristics of the embankment and foundation. Without geofoam, unit weight of the embankment fill is equal to 18 kilonewton per meter cube. Unit weight of foundation soil is 18 kilonewton per meter cube. Height of the embankment including the pavement covering HE is equal to 5 meter. Thickness of the pavement covering is equal to 0.6 meter. Liquid limit is equal to 60%. Thickness of compressible layer, that is HP, is equal to 12 meter, and unit weight of pavement layer is equal to 19 kilonewton per meter cube. So, this is the embankment construction without the geofoam. This is the embankment fill whose density is given 18 kilonewton per meter cube, and this is the foundation soil, and this unit weight of foundation 18 kilonewton per meter cube, and void ratio E0 is 0.65, liquid limit 60%, and Cc value is equal to 0.45 and depth of the foundation 12 meter and the height of the embankment is 5 meter. So, with geofoam, so height of the geofoam embankment HE is 5 meter, unit weight of geofoam is 0.18 kilonewton per meter cube. Here you can see that unit weight of geofoam is 100 times less than the unit weight of the soil. So, we have to calculate the settlement of the embankment without and with geofoam. So, we will observe that what will be the settlement when there is no geofoam and what will be the settlement when there is a geofoam. Now, here I just wanted to point out that here is a unit weight of the pavement covered because its density is different. So, this is gamma Pc is equal to 19 kilonewton per meter cube, and this is thickness. This pavement asphalt covered system is 0.6 millimeter, 6 meter, and this height is 4.4 meter. So, total will be equal to 5 meter. So, now the solution. You know Cc is equal to 0.009 into liquid limit minus 10. So, is equal to 0.009 and liquid limit is 60 is given, minus 10 is equal to 0.009 into 50 is equal to 0.45. Now, Holz and Kovacs 1981 reported the settlement as S is equal to Cc into H divided by 1 plus E0 into log of P0 plus delta P by P0, where S is equal to settlement, H is equal to thickness of compressible soil layer, E0 is void ratio of compressible soil layer, and P0 is existing pressure at the mean height of the compressible soil layer, and delta P is the embankment load due to the settlement. So, when you are not using the geofoam, so without geofoam, so at mid height of the compressible layer, so what is P0? So, P0 is equal to the gamma f into h by 2, and gamma f is given 18 and height of the foundation is 12. So, 18 into 12 divided by 2, that means 18 into 6 is equal to 108 kilonewton per meter square. So, at the mid height of the compressible layer, that is P0 is equal to 108 kilonewton per meter square. What you know, the H is equal to thickness of compressible layer. Now, what is delta P? So, delta P is equal to gamma E into He. You know the height of the embankment is 5 meter and unit weight of the embankment is 18 because it is a soil. So, his density is 18 kilonewton per meter cube because there is no geofoam. So, it will be 18 into 5 is 90 kilonewton per meter square. Here He is equal to height of embankment. Now, settlement of embankment without geofoam, that means this is Cc into, you know this equation, Cc into h by 1 plus E0. So, it will be the Cc is 0.45, okay, h is 12 meter, this divided by 1 plus E0 and E0 value is given 0.65. So, 1 plus 0.65 into log of P0 plus delta P by P0. So, here this is the equation we are using, P0 plus delta P by P0. So, you know that what is that P0 is 108 and delta P is 90. So, we are substituting this here, log of P0 is 108 plus delta P is 90. This divided by P0 108, where we have obtained from here P0 and delta P 90 kilonewton per meter square. So then you can have 5.4 divided by 1.65 into log of 198 by 108, that is equal to 3.27 into log of 1.8333, so is equal to 3.27 into 0.263 is equal to 0.86 meter. So you see that settlement of the embankment without geofoam is equal to 0.86 meter. Now we will calculate that what should be the settlement with the geofoam. Now with geofoam we have to calculate what is delta of P. So delta of P is equal to gamma of G into He plus gamma of F into Hp. So here the density or unit weight of the geofoam is 0.18 and He is 4.4. I showed you that what is He is 4.4 plus that, because on the top here that asphalt overlay is there, the density is 19 and Hp is 0.6. So I am just showing you here again. Here you can see this is the 4.4 and density is 0.18 kilonewton per meter cube. So 4.4 into 0.18 kilonewton per meter cube for this part, and this part unit weight of the pavement cover where gamma PC is 19 kilonewton per meter cube and this thickness is 0.6. So 0.6 into 19 kilonewton per meter cube. So that's why it has written that 0.18 into 4.4 plus this is gamma is 19 into Hp is 0.6. So you can obtain is equal to 0.792 plus 11.4 is equal to 12.192 and let us say approximately 12.2 kilonewton per meter square. So here I say that H is the height of the embankment and Hp is the height of the pavement layer on the top. Now we know this equation, that is H is equal to Cc into H by 1 plus E0 into log of P0 plus delta P by P0. So S is equal to 0.45 into 12 divided by 1 plus E0 is 0.65 into log of that P0 plus delta P, that means 108 plus delta P here is 12 divided by 108. So this will give approximately the settlement is 0.154 meter. So you can see when you are using the geofoam, settlement is 0.154 meter. When the only soil without geofoam, the settlement is 0.86 meter. So reduced settlement due to the application of geofoam will be equal to 0.86 minus 0.154 meter, that means 0.706 meter, or you can say that reduced in settlement due to the geofoam is 0.706 divided by 0.86 is equal to 82.09 percentage. So you can see that how drastically the settlement has been reduced due to the application of the geofoam material. So now we will discuss the application of geofoam as a compressible inclusion. Horvath 1991, 1997 and Nibalkar 1999 have reported that the inclusion of the geofoam on the back of the retaining wall reduced the lateral earth pressure even less than the active state. So, we have also performed number of tests on the centrifuge using the geofoam for the retaining wall, where geofoam has been used as a compressible inclusion. Lateral earth pressure depends upon the thickness of the geofoam. The more the thickness of the geofoam mean the more the reduction of the lateral earth pressure, even almost zero earth pressure. I will give later one example on it. You can see here that vertical geofoam embankment field, and this is the road which is made of the geofoam. So, horizontal pressure acting on the retaining wall can be expressed as sigma h is equal to k into sigma b, where sigma b is equal to vertical pressure, k is equal to coefficient of earth pressure. As you know, at rest k0 is equal to 1 minus sin phi as per Jackie, where k0 is equal to coefficient of earth pressure at rest condition, and pi is friction angle of backfill soil. At active state, k is equal to k is equal to 1 minus sin pi divided by 1 plus sin pi, where Ka is coefficient of active earth pressure. Now, this is some work in our geosynthetic testing laboratory, and we have used the centrifuge and have performed the test. This is the reduced lateral displacement of the wall with increase in geofoam thickness. This Nibalkar 1999. So, this is the wall displacement versus the wall height. The height of the wall is about 8, and this is the centimeter, and this is the wall displacement is about 20 millimeter. And here the geofoam here use the 23 kg per meter cube, and when you use only as a backfill material, this is the nature of the curve. You can have it, this wall height with respect to the displacement. But in case 2, when you are using the geofoam thickness is h by 20, that is 4 millimeter. That means h is the height of the wall. Okay? So, that means if the height of the wall is 8, so 8 by 20 will be equal to 4 millimeter. So, next is the 3, when the geofoam thickness is equal to h by 10. That means h is equal to 8, 8 by 10 is equal to 8 millimeter. Then in number 4, so this is geofoam thickness h by 5, that means 8 by 5 will be 16 millimeter. So, you can see that how it is increasing the thickness and displacement is reducing gradually. So, more the thickness and less the wall displacement by the inclusion of the geofoam material. Now, I will explain one example. Let us say height of the retaining wall H is equal to 8 meter. Unit weight of backfill soil is equal to 18 kilonewton per meter cube. Angle of friction of backfill soil pi is equal to 32 degree. Now determine the lateral earth pressure at the following condition. A. Active condition without geofoam. B. Using the geofoam of thickness 4 millimeter, 8 millimeter and 16 millimeter. So let us say this is the wall, cantilever retaining wall, here is a geofoam and this is the backfill material. We will change this thickness of the geofoam material and we will observe that how the lateral pressure either it is increasing or the decreasing by the inclusion of the different thickness of the geofoam material. So here is the solution, the active condition only backfill. So the lateral pressure at active condition, that is Pa, is equal to half into Ka into gamma H square, where K is coefficient of active earth pressure is equal to tan square 45 degree minus pi by 2. So pi value is equal to 32 degree. So tan square into 45 degree minus 32 degree by 2 is equal to tan square 29 degree is equal to 0.307. So K is 0.307. Therefore, Pa, that is lateral pressure at active condition, is equal to half into K value is 0.307 into gamma value is 18 and H is the height of the wall is 8. So this is 8 square. So this Pa value will be 176.832 kilonewton per meter. So now we will use the geofoam. So you have to calculate the area of the lateral displacement diagram have been calculated based on this following figure. Now area under the active curve, so here this is 8. So from here to here is 20. This is 20 and this is 8 centimeter and this is 20 millimeter. So in case of here 1, so area under the active curve, that means half into this is 20 into 80. So this will give 800 millimeters square. So this is area under active curve. Now the area under 4 millimeter curve. So when you are considering 4 millimeter curve, that means the thickness of the geofoam is 4 millimeter. So for the 4 millimeter, your wall displacement somewhere here 6.25. So this area will be equal to half into 6.25 into 80. So this will give 250 millimeters square. Now if we use the 8 millimeter thickness of the geofoam, so that means we will take this area 3, this area. So here this will give you about 3.75. So area will be half into 3.75 into 80. So this will give 150 millimeter square. Now if you use 16 millimeter thickness of geofoam, that means this 4. So this length will be equal to 1.45. So this is 1.45, that means half into 1.45 into 80 is equal to 58 millimeter square. So you can see here that inclusion of the geofoam, this area is reducing, increasing the thickness of the geofoam, the area is gradually it is reducing from when there is no geofoam, this is 800 millimeter square, and when you are providing 4 millimeter thickness of geofoam, then it is 250 millimeter square area. When it is 8 millimeter thickness of geofoam, the area is 150 millimeter square, and again when you are providing 16 millimeter thickness of geofoam, this area is coming 58 millimeters square. Now case 1, geofoam of 4 millimeter thickness. So what is the pressure for 4 millimeter thick geofoam? Let us say P4 is equal to area of 4 millimeter curve divided by area of active curve into 176.832. That means area of 4 millimeter curve you have calculated that what is area of 4 millimeter curve, that is 250 here. So this is 250. This divided by area of active curve, this is 800 millimeter square. So 250 by 800 millimeter square into 176.832, which we have calculated earlier here. This is the lateral pressure at the active condition, 176.832. So that's why here 176.832. So for the pressure for 4 millimeter thick geofoam, so you can write that 55.26 divided by 176.832 is equal to 31% of active. Now we consider case 2 where 8 millimeter thick of geofoam have been used. So what will be the pressure for 8 millimeter thick geofoam? So that we express as P of 8 is equal to area of 8 millimeter curve divided by area of active curve into 176.832. So you know for the area of 8 millimeter, that is 150 millimeter square, and area under active 800 millimeter square. So we can write 150 divided by 800 into this, you know, 176.832. So this will give 33.156 kilonewton per meter. So here you can see that 33.156 divided by 176.832, that means 19% of the active. So here you see when 4 millimeter thickness of geofoam used, that is 31% of the active, but when you use the 8 millimeter thickness, this is 19% of the active. It is gradually this decreasing with the increase of the thickness of the geofoam material. Now case 3, 16 millimeter thickness of geofoam. The pressure for 16 millimeter thick geofoam, that is P16, is equal to area of 16 millimeter curve divided by area of active curve into 176.832. here area of 16 millimeter, you can see that area under 16 millimeter 58 millimeter square. So that is why 58, and you know area of active curve is 800 into 176.832. So this will give P16 is equal to 12.82 kilonewton per meter. Now 12.82 divided by 176.832 is equal to 7% of the active. So evidently it can be observed that lateral earth pressure reduced significantly with the increase in the thickness of geofoam. So overall you can have some idea that how the inclusion of the geofoam can reduce the lateral pressure drastically. Now here the geofoam in between the expansive soil and this is the concrete, this is the soiling soil, and this is the concrete slab of the footing of a building. This is the building, this is the concrete slab, and below the concrete slab you can provide with the geofoam material. So there will be no crack of the building. There is a upward thrust from the soiling soil, and how you can reduce, how it can be prevented by the placement of the geofoam material below the concrete slab. So here as the geofoam is a compressible inclusion, so it can be placed over the expansive soil beneath the concrete slab of the footing of a building. So example 3, the maximum allowable stress developed below the concrete slab of a building foundation from soiling is 40 kilopascal, causing the deformation of 12 millimeter. So you have to determine what should be the required thickness of the geofoam to prevent it. So here in this problem we will calculate the what thickness is required due to that soiling and the deformation. So there is a solution. For the soiling pressure or the compressive stress of 40 kilopascal, the compressive strain of geofoam is 25% as obtained from the rapid loading test as shown here. So this is the curve, the stress strain behavior of the geofoam block of density of 23 kg per meter cube in rapid loading test, the Nimal curve 1999. So here you can see that what will be the axial compressive stress in kilopascal, and here is the axial compressive strain in terms of the percentage. So this is the rapid loading test. So you know that in your problem that 40 kilopascal. So you check from this curve for the 40 kilopascal what will be the axial compression strain. So here is the axial compression strain. It lies between 20 and 30, so it will be 25%. So that's why 40 kilopascal the compressive strain of the geofoam is 25%. So you can obtain from this rapid loading testing that what should be the strain for that compressive state. In our problem we have a that compressive stress is 40 kilopascal, so corresponding stress is 25. So for any other problem also you can calculate that what will be the strain and corresponding to the compressive state. So required thickness of the geofoam, that is design magnitude of surface deformation divided by geofoam strain in percentage into 100. So you know that design magnitudes of the surface deformation is 12. So, which we have obtained, and this divided by geofoam strain is this 25, which you find out, and this deformation is given the 12 in the problem. Here is the deformation is given, that for this swelling pressure of 40 kilopascal, the deformation is 12 millimeter. So, you know this is 12 millimeter, and you calculate that for this 40 kilopascal, this compressive strain is 25%. So, 12 divided by 25 into 100 is equal to 48 millimeter. So, this design of geofoam is cost effective for expansive soil. So, you know that how you can use the geofoam for the below the building or the foundation, and here you can see that some of the application, that is putting pressure, how it is reducing. Here is the geofoam has been introduced, and here you can see that how the heap pressure also reduction the field, how the geofoam has been used. So, define type of the geofoam, and it depends upon the density, also it depends upon that what will be the density of the geofoam and as well as the thickness of the geofoam. And you should know for a particular the density what should be the thickness and how to calculate the thickness of the geofoam. This is very important. Either you use on the back of the retaining wall, or you use at the base of the foundation soil where there is a swelling soil, and you can see that how pressure can be reduced drastically. So, you have an overall some idea that how geofoam inclusion can reduce the lateral pressure, where the geofoam material act as inclusion, and on the other hand how you can reduce the also the settlement, and as well as the swelling pressure can be reduced, and how you can determine the thickness of the geofoam material. With this I finish my lecture today. Let us hear from you any question. Thanks for listening.